Hi everyone, today we are going to study two very important topics in graph theory. One is the in degree and out degree of vertices and other is parallel edges. So this in degree and out degree and parallel edges we would be studying in reference to the directed graphs or the digraphs. Now we'll start with in degree and out degree of vertices. So basically you know that in a directed graph there are directed edges. That means arrows are on the edges and the direction of the arrow tells you that in which direction that particular edge is going. When I say in which particular direction that edge is going, that means from which particular vertex to which particular vertex that edge is going. Right? So the vertex from which an edge goes out. Like here in case of vertex V1 and V3, you can see that edge E1 is incident upon vertex V1 and V3. Apart from being incident on vertex V1 and V3, edge E1 is going out of vertex V1. The direction of the arrow clearly shows that edge E1 is going from vertex V1 and going to vertex V3. So the vertex from which an edge goes out, the edge is said to be incident out of that vertex. Here, edge E1 is incident out of vertex V1. And the vertex into which the edge goes, then that edge is said to be incident into that vertex. Like here, E1 is incident into vertex V3. So this is the concept of incident into and incident out of. Edge E1 is incident out of vertex V1. Edge E1 is incident into vertex V3. So in degree and out degree are the terms which are related to this thing only. So what is first of all out degree? The number of edges incident out of a vertex Vi is called the out degree or out valence of a vertex Vi. So this is the concept of out degree, that from a vertex, the number of edges which are incident out of that particular vertex would be known as the out degree of that vertex. The number of edges incident out of a vertex Vi is called the out degree or out valence of Vi. Out degree is also known as out valence. How do you denote out degree? D, a positive sign within brackets Vi. Here D represents the degree. A positive sign shows that we are talking about out degree, and Vi is that particular vertex whose out degree we are talking of. Right? So this is how you denote the out degree. Now let's talk of in degree. The number of edges that are incident into a vertex is called the in degree or in valence of that vertex. Like here you can see so the number of edges, the number of edges that are incident into a particular vertex, that would be known as the in degree or in valence of that particular vertex. So the number of edges incident into a particular vertex Vi is called the in degree or in valence of that particular vertex Vi, and is written as D, a negative sign, and Vi. D again here represents the degree of that particular vertex. A negative sign shows that we are talking of in degree, and Vi is that particular vertex whose in degree we are talking of, right? So this is how you define the in degree and out degree of a particular vertex. It's a very simple concept. In degree means number of edges incident into a particular vertex, and out degree means number of edges incident out of a particular vertex. Now if we take this particular example, this particular graph, we can find the in degree and out degree of certain vertices. Like for here, the out degree, a positive sign always means out degree and a negative sign always means in degree. So if you consider vertex V1, the out degree of vertex V1 is 3. How? That means how many edges are incident out of vertex V1. So you can see that there are 3 edges which are going out of vertex V1. Edge E4 is going out of vertex V1. Edge E1 is going out of vertex V1. Edge E2 is also going out of vertex V1. And there is no other edge which is going out of vertex V1. So 1, 2, 3. In total, how many edges are incident out of vertex V1? 3 edges. Hence the out degree of vertex V1 is 3. Now again, if we consider the in degree of vertex V1, that means we are considering how many edges are incident into V1. So the in degree of vertex V1 is 1 because there is only one edge E3 which is incident into vertex V1. Now if I consider vertex V2, what is the out degree of vertex V2? It is 1. Why? Because V2, the vertex V2 has a self loop. Now you know that a self loop is such an edge which starts from that particular vertex and it ends also at that particular vertex only. That means for a self loop, an edge is incident into also the same vertex and incident out of also the same vertex. So here, since we are talking about the out degree, so we will see incident out of. So you can clearly see for vertex V2 there is only one edge which is incident out of or incident out of your vertex V2, which is edge E5. Hence the out degree is 1. Now if we consider the in degree of vertex V2, again the same edge E5 is incident into V2 also. So E5 is incident into V2. So again we have only one edge which is incident into V2. So the in degree of vertex V2 is 2. If I consider vertex V5, the out degree of vertex V5 is 4. Why? If you look at vertex V4, you can see that there are 4 edges which are incident out of vertex V5. Clearly, the direction of arrows shows you that all these edges are incident out of vertex V5. Like edge E10 is incident out of vertex V5, edge E9 is incident out of vertex V5, edge E8 is incident out of vertex V5, and edge E7 is incident out of vertex V5. So in total, how many edges? 1, 2, 3 and 4 edges are incident out of V5. Hence, the out degree of vertex V5 is 4. Now what is the in degree of vertex V5? The in degree of vertex V5 is 0. Why? Because there is no edge which is incident into vertex V5. If you look at vertex V5, there are total 4 edges which are incident upon V5, and all those 4 edges are incident out of vertex V5. None of them are incident into vertex V5. So there is no edge basically which is incident into vertex V5. Hence, the in degree of vertex V5 is 0 here. So this is how you find the in degree and out degree of any vertex in a directed graph. See, whenever I talk of in degree and out degree, I am always talking of your directed graph. Right? You cannot have in degree and out degree in an undirected graph, because in an undirected graph there are no directed edges. The edges are not directed. That means there is no arrow on the edges which would be showing you the direction of edges, that is from which particular vertex that edge is going out and to which particular vertex that edge is going into. So in an undirected graph, there are no directed edges. When there are no directed edges, you cannot find out from which vertex that edge is going out of and into which vertex that edge is going into. So hence there is no question of in degree and out degree. When I talk of undirected graphs, I only say that this particular edge is incident upon this particular vertex. I never say it is incident out of this particular vertex. I never say it is incident into that particular vertex. So there is no question of in degree and out degree in an undirected graph. We talk of the in degree and out degree of a vertex only in case of a directed graph. And this is how you can find the in degree and out degree in a directed graph. Now, an isolated vertex is a vertex. When we are talking of in degree and out degrees, so we can easily find out whether a vertex is an isolated vertex or not by seeing its in degree or out degree. So it says that an isolated vertex is a vertex in which the in degree and the out degree are both equal to 0. Now you all know the concept of isolated vertex. Any such vertex which is isolated, that means no edge is incident upon that vertex, is an isolated vertex. So it is quite obvious when no edge is incident on that particular vertex, that means there is no in degree or out degree of that vertex, right? And when there is no in degree or out degree of that vertex, obviously it will be the in degree or the out degree. That means both the in degree and out degree of that particular vertex would be 0. Like here, if you consider this particular graph with 3 vertices v1, v2 and v3. Now v1 and v2 have an edge between them, but if you look at vertex v3, there is no edge incident upon v3, right? When there is no edge incident upon vertex v3, so there is no question of in degree and out degree. So if I want to find out the in degree of v3, what would be the in degree? It would be 0. Similarly, if I want to find out the out degree of vertex v3, what would be its out degree? It would be 0 again. So an isolated vertex always has the in degree and out degree both has 0. So that means if you find any such vertex whose in degree and out degree are both equal to 0, you can say that it is an isolated vertex. Similarly, a vertex V in a directed graph or digraph is called pendant if it is of degree 1. That is, if either the out degree is 1 or the in degree is 1. Now, pendant vertex also, you know, is one such vertex in which there is only one edge, on which there is only one edge incident. So, if you look at this graph, there are how many vertices? 5. Edge V, edge V1, edge V2, edge V3 and edge V4. Now, if you look at edge V, there are 2 edges incident upon edge V. If you look at edge V1, there are 2 edges incident upon edge V1. If you look at edge V2, there are 2 edges incident upon edge V2. If you look at edge V3, there are 2 edges again incident upon edge V3. But if you look at edge V4, there is only one edge incident upon vertex V4, right? And this edge is incident out of vertex V4. So that means if this edge is incident out of vertex V4, that means the out degree of vertex V4 is 1. Now there is no edge which is incident into vertex V4, hence the in degree of vertex V4 is 0. So either the out degree will be 1 or the in degree would be 1, but both cannot be 1. So either the out degree is 1 and the in degree is 0, or vice versa, the in degree would be 1 and the out degree would be 0 in case of a pendant vertex. Obviously, it is pendant because it has only one edge incident upon it. And if there is only one edge incident, it is quite obvious that either the in degree will be 1 or the out degree will be 1. So that is why a pendant vertex has either the out degree as 1 or in degree as 1. So for that reason, whenever you see a vertex which has either the out degree as 1 or the in degree as 1, but not both as 1, then you can say that that particular vertex is a pendant vertex. Now, we will look at parallel edges in directed graph. We have seen parallel edges in undirected graphs. So, in case of directed graphs, 2 directed edges are said to be parallel if they are mapped onto the same ordered pair of vertices. This is one condition. This is one condition that in a directed graph, 2 edges are said to be parallel if they are mapped onto. That means that if they are incident upon the same pair of vertices. And this condition applies for undirected graphs also. In undirected graphs also, we say that 2 edges are parallel if they are incident upon the same pair of vertices. So is the condition in case of directed graphs also, that 2 directed edges are said to be parallel if they are incident or mapped onto the same pair of vertices. But this is just one condition. The other condition here is that in case of directed graphs, the other condition is that in addition to being parallel, in addition to being incident upon the same set of vertices, they must also agree in the direction of their arrows, right? So that means when we talk of unordered graphs, we only need to be concerned about the fact that these 2 edges are incident on the same pair of vertices, then they are parallel. But when we are talking of directed graphs, we need to see first of all that the directed edges must be incident upon the same pair of vertices, and then they must also agree in the direction of their arrows. That means the direction of their arrows must also be same. For example, if you consider this graph, you can see that edges E8 E9 and E10 are incident upon the same pair of vertices, V3 and V5. All these three edges are incident upon the same pair of vertices V3 and V5. So one condition is satisfied. Now we have to see if they have the same direction of arrows also. And clearly you can see that ET, E8, A9, E9 and E10. All three are having the same direction of arrows. So hence E8, E9 and E10, all three of them are parallel edges. Now if you consider the edges E3 and E2, again they are also incident upon the same pair of vertices, right? Both E3 and E2 are incident upon vertex V1 and V4. But if you look at the direction of arrows, they do not have the same direction of arrows. E3 is incident into vertex V1 and E2 is incident out of vertex V1. Clearly they do not have the same direction of arrows. Hence E3 and E2 are not parallel edges. But if this was a case of undirected graph, then E3 and E2 would also have been parallel edges, because there this arrow would not have existed, and without the arrow, in case of an undirected graph, the only condition that we have to see is that if they are incident upon the same pair of vertices. So if we consider an undirected graph, then E3 and E2 are also parallel edges. But since we are considering a directed graph, clearly you can see both the edges E3 and E2 have arrows on them which is showing the direction of the edges, and clearly you can see that the arrows are not in the same direction for these two edges, despite the fact that they are incident on the same pair of vertices. Hence clearly E3 and E2 are not parallel edges.